So here's something worth thinking about as you settle in tonight. Right now, wherever you are, whatever bed or couch or comfortable spot you've found, you are sitting on a planet that is mostly not land. That sounds obvious when you say it out loud, but really sit with it for a second. If you could somehow drain all the water out of the ocean basins and stand at the edge and look down, you'd be staring at a landscape more dramatic than anything on the surface. Mountain ranges longer than the Andes, trenches deep enough to swallow Mount Everest with room to spare, vast, flat plains of sediment stretching for thousands of miles, so featureless they make the Sahara look busy, and all of it hidden. All of it working away beneath this enormous, restless, interconnected body of water that covers about 71% of the Earth's surface. We live on an ocean planet. We just happen to cling to the dry parts. And here's what's wild. For most of human history, we had almost no idea how any of it worked. The oceans were just there. Big, terrifying, useful for fishing, occasionally crossable if you were brave or desperate enough. But the actual mechanics of the thing, why currents flow the way they do, why some water is warm and some is freezing, why the tides rise and fall with such stubborn regularity, what lies down in the deep, how the ocean shapes our weather and our climate and, honestly, the entire trajectory of civilization. All of that was a mystery. And peeling back that mystery has been one of the great, slow-burning adventures of science. It's taken thousands of years, and we're still not done. Not even close. So tonight, let's just talk about it. All of it. How the oceans work. We'll start at the very beginning. And I mean the very beginning, like how there even came to be oceans in the first place. And we'll work our way forward through time, through discovery, through the people who figured things out, and the people who got things spectacularly wrong. There's no rush. If you drift off somewhere along the way, that's perfect. That's kind of the point. But if you stay with me, I think you'll find that the ocean is one of the most fascinating machines on Earth. Because that's really what it is. A machine, a heat engine, a chemical reactor, a conveyor belt, a climate regulator, a biological engine of almost incomprehensible scale. And it all runs on physics. Beautiful, elegant, sometimes counterintuitive physics. Let's start with water itself, because you can't understand the ocean without understanding why water is so strange. And it is strange. Water is one of the weirdest substances in the known universe, and we only think it's normal because we're surrounded by it. Here's what I mean. Most liquids, when they freeze, they get denser. The solid form sinks in the liquid form. That's what you'd expect, right? Molecules slow down, pack tighter, the solid is heavier. But water does the opposite. When water freezes, it expands. Ice is less dense than liquid water. That's why ice floats. And you might think, okay, that's a fun fact for a cocktail party. But think about what that means for the planet. If ice sank, every lake, every river, every ocean, in a cold climate, would freeze from the bottom up. The ice would sink. More water would be exposed to the cold air that would freeze and sink too. And eventually, you'd have solid ice with maybe a thin layer of liquid on top in summer. Life in those waters would be crushed, frozen, finished. Instead, ice floats, forms an insulating layer on top, and the water beneath stays liquid. Fish survive the winter. The ocean doesn't freeze solid at the poles. Life goes on. That one quirky property of the water molecule, the way hydrogen bonds form a crystalline lattice that spaces the molecules slightly farther apart in solid form, that one thing might be the reason complex life exists on this planet at all. And water's weirdness doesn't stop there. It has an unusually high specific heat capacity, which is a fancy way of saying it takes a lot of energy to change its temperature. Think about a summer day at the beach. The sand is scorching hot under your feet, right? You can barely walk on it. But the water is cool, pleasant, hasn't changed much at all even though the same sun has been beating down on both of them all day. That's because water absorbs enormous amounts of heat without its temperature rising very much. And this matters for the ocean in a profound way, because it means the ocean is the planet's great thermal buffer. It absorbs heat from the sun during the day and in summer, stores it, and releases it slowly. Coastal cities have milder climates than inland cities at the same latitude. London is at roughly the same latitude as Calgary, Canada, but London rarely sees the brutal winters Calgary does, and a huge part of that is the Atlantic Ocean and the currents that bring warm water up from the tropics. The ocean is smoothing out the temperature extremes that would otherwise make much of the planet uninhabitable. Water also has a very high latent heat of evaporation. That means it takes a tremendous amount of energy to turn liquid water into water vapor. When the sun evaporates water from the ocean surface, all that energy gets locked into the vapor, carried up into the atmosphere, and released somewhere else when the vapor condenses back into liquid, into clouds, into rain. This is the engine that drives weather. This is where hurricanes get their terrifying power. A hurricane is essentially a heat engine that feeds on warm ocean water. The warmer the water, the more evaporation, the more energy pumped into the storm. That's why hurricanes form over tropical oceans and weaken over land. They're literally running out of fuel. But okay, let's step back. Way, way back. How did the oceans get here in the first place? This is one of those questions that seems simple and turns out to be wonderfully complicated. For a long time, the leading theory was pretty straightforward. The early Earth was incredibly hot, a molten ball of rock and metal, and as it slowly cooled over hundreds of millions of years, water vapor that had been trapped in the interior, dissolved in the magma, locked in the minerals, gradually outgassed through volcanic eruptions. Volcanoes belched out enormous quantities of steam, carbon dioxide, nitrogen, and other gases. The steam rose, cooled, condensed, and fell as rain, and it rained and rained for millions of years, slowly filling the basins that would become the oceans. It's a dramatic image. This hellish young planet shrouded in thick clouds, lightning cracking through an atmosphere of volcanic gases, rain falling on rocks so hot it would have flashed back to steam at first until the surface finally cooled enough for liquid water to accumulate. And that's probably part of the story. But in the last few decades, another piece of the puzzle has gotten a lot of attention: comets and asteroids. During the late heavy bombardment, roughly 3.8 to 4.1 billion years ago, the inner solar system was getting absolutely pummeled by leftover debris. And comets, in particular, are essentially dirty snowballs. Ice and dust and frozen gases. The idea is that a significant fraction of Earth's water might have been delivered from space, carried in by these icy impactors. Scientists have tested this by looking at the ratio of regular hydrogen to deuterium, that's heavy hydrogen, hydrogen with an extra neutron, in ocean water, and comparing it to the ratios found in different types of comets and asteroids. And here's what's interesting. The ratios in Earth's oceans match certain types of carbonaceous chondrite asteroids much better than they match most comets we've measured. So the current thinking is that it was probably a mix, some water outgassed from the interior, some delivered by asteroids, maybe a smaller contribution from comets. But the exact proportions are still debated. We're still figuring it out. And that's kind of beautiful, honestly. We live on this planet, We drink this water every day, and we're still not entirely sure where it came from. What we do know is that by about 3.8 billion years ago, there were oceans, liquid water on the surface. We know this because of tiny crystals called zircons, incredibly durable minerals that survive even when the rocks around them are destroyed and reformed. Some zircons found in Western Australia, in a place called the Jack Hills, have been dated to about 4.4 billion years old, and their chemical signatures suggest they formed in the presence of liquid water, so the oceans might be even older than we thought, almost as old as the Earth itself, and those early oceans would have been unrecognizable to you. The water was probably greenish, maybe even slightly acidic, rich in dissolved iron. There was no free oxygen in the atmosphere. That wouldn't come for another billion years or so, not until photosynthetic organisms started pumping it out. The sky might have been orange or pinkish, thick with methane and carbon dioxide. No continents as we know them, just volcanic islands and maybe some small proto-continents poking above the waves. And the moon was much closer to Earth than it is now, which means the tides were enormous, perhaps hundreds of feet in some places, surging in and out with tremendous force. Some scientists have speculated that those intense tides might have played a role in the origin of life itself, repeatedly wetting and drying tidal pools, concentrating chemicals, driving reactions. It's speculative, but it's a lovely thought. The ocean's own rhythm, its breathing in and out, might have been the cradle. Now, the people who first started trying to understand the ocean in any systematic way, they didn't have any of this deep-time perspective, of course. For the ancient Polynesians, the Phoenicians, the Greeks, the Chinese, the Arabs, the Norse, the ocean was a practical problem. How do you cross it? How do you navigate it? Where are the fish? What makes the tides go in and out? And their answers were a fascinating mix of brilliant observation and total mythology. The Polynesians might be the most remarkable ocean observers in human history. Starting roughly 3,000 years ago, maybe earlier, they colonized islands scattered across the vast Pacific, an area covering millions of square miles of open water, using double-hulled canoes and navigational techniques that still astonish scientists today. They read the stars, yes, but they also read the ocean itself. They could detect the subtle bending of swells around islands that were still far beyond the horizon. They watched the behavior of birds, the color of the water, the patterns of clouds that form over land. They understood, intuitively and practically, things about wave refraction and diffraction that Western science wouldn't formalize until centuries later. And they passed this knowledge down orally, through chants and stories and apprenticeships that could last decades. No charts, no instruments, no written language in many cases, just an extraordinarily deep, embodied understanding of how the ocean moves. The Greeks, meanwhile, were asking different questions. Aristotle, around 350 BCE, wrote about the ocean in several of his works. He knew the Mediterranean was saltier in some places than others. He speculated about why the sea is salty, not entirely correctly, but he was thinking about it. He observed marine life with remarkable care, describing species that wouldn't be scientifically classified for another 2,000 years. But it was Pytheas of Massalia, a Greek explorer from what is now Marseille, who made one of the first truly important oceanographic observations in the Western tradition. Around 325 BCE, Pytheas sailed north, way north, probably as far as Iceland or Norway, and he noticed something that would puzzle scientists for centuries. He noticed that the tides in the Atlantic were much larger than the tides in the Mediterranean, and he connected them to the phases of the moon. The tides follow the moon. It sounds obvious now, but at the time, it was a genuine insight, and not everyone believed him. Many of his contemporaries thought he was a liar. His original account is lost. We only know about it through later writers who quoted him, often dismissively. And the tides. Let's talk about the tides for a moment, because they're one of those things that seem simple on the surface, but get beautifully complicated when you dig in. You probably know the basic idea. The moon's gravity pulls on the earth, and it pulls on the water more than on the solid ground because water is free to move. So you get a bulge of water on the side of the earth facing the moon. High tide. Makes sense, right? But here's the part that trips people up. There's also a bulge on the opposite side of the earth, the side facing away from the moon. Why? If the moon is pulling water toward it on one side, why would there be a high tide on the far side too? And the answer has to do with the way gravity works across distance, combined with the fact that the Earth and Moon are actually orbiting around a common center of mass. On the near side, the Moon's gravitational pull is stronger than average. Water gets pulled toward the Moon. On the far side, the Moon's pull is weaker than average, and the centrifugal effect of the Earth-Moon system's rotation flings water outward. So you get two bulges, two high tides, roughly every 24 hours and 50 minutes. The 50 minutes accounts for the fact that the moon is also moving in its orbit, so the Earth has to rotate a little extra each day to catch up. And then you add in the sun, which also exerts a gravitational pull on the oceans. When the sun and moon are aligned, during new moons and full moons, their tidal forces add together, and you get especially large tides called spring tides. When they're at right angles to each other, during quarter moons, the forces partially cancel, and you get smaller tides called neap tides. But even that is a simplification, because the real ocean doesn't behave like a smooth, uniform layer of water on a smooth, uniform sphere. The continents get in the way. The ocean basins have complicated shapes. The water has inertia. It can't instantly rearrange itself in response to the gravitational forces. So what actually happens is that tides propagate as enormous, very long wavelength waves that slosh around the ocean basins, and the timing and height of the tide at any particular coastline depends on the shape of the basin, the depth of the water, the geometry of the coast, and a dozen other factors. Some places, like the Bay of Fundy in eastern Canada, have tidal ranges of over 50 feet because the shape of the bay creates a resonance effect. The natural period of water sloshing back and forth in the bay happens to nearly match the tidal period, so the tides get amplified, like pushing a child on a swing at just the right moment. Other places, like some parts of the Mediterranean, have tides of just a few inches. And this is something you'll notice as we go along tonight. The ocean is full of these resonance effects, these feedback loops, these cases where geometry and physics conspire to create something much bigger or much stranger than you'd expect from the basic principles alone. The ocean is simple in its ingredients: water, salt, heat, gravity, the spinning of the earth. But the way those ingredients interact produces a system of almost infinite complexity, and humans have been trying to untangle that complexity for a very long time. One of the earliest attempts to map the ocean's behavior in a truly systematic way came from an unlikely source. A man who never actually went to sea as a scientist, who was bedridden for much of his career, and who assembled one of the most important oceanographic datasets in history, essentially by writing letters. His name was Matthew Fontaine Maury, and he was working out of the United States Naval Observatory in Washington, D.C., in the 1840s and 1850s. But to understand what Maury did, and why it mattered so much, you need to understand what sailors already knew and didn't know about the great currents and winds that govern the world's shipping lanes. Because by the 1840s, sailors had centuries of accumulated practical knowledge about the ocean. They knew, for instance, that if you were sailing from Europe to the Caribbean, you didn't sail in a straight line. You dropped south first, picked up the trade winds blowing steadily from the northeast, and let them carry you westward. They knew about the doldrums near the equator, that maddening belt of calm where the wind just died and ships could sit becalmed for days or even weeks. They knew about the Gulf Stream. Benjamin Franklin had actually published a chart of it back in 1769, based on information from his cousin Timothy Folger, a Nantucket whaling captain who understood that this warm river of water flowing through the Atlantic was why westbound mail packets from England took weeks longer than eastbound ones. Whalers knew the Gulf Stream intimately because whales tended to feed along its edges, where the warm and cold water mixed and nutrients concentrated. So the knowledge was out there, scattered across thousands of logbooks and the memories of thousands of captains, but nobody had ever pulled it all together. And that's exactly what Maury decided to do. His story is one of those wonderful cases where personal misfortune redirected someone's energy in a way that changed the world. Maury had been a promising naval officer, but in 1839, at the age of 33, he was badly injured in a stagecoach accident that left him with a dislocated knee and a broken leg that never healed properly. He couldn't go back to sea. Instead, he was assigned to run the depot of charts and instruments, which eventually became the Naval Observatory. And there, surrounded by dusty shelves of old ship logbooks that nobody had ever bothered to analyze systematically, Maury had an idea. Every ship that sailed under the American flag kept a logbook. Every day, the captain recorded the ship's position, the wind direction and speed, the currents they encountered, the water temperature, the weather. Decades of logbooks were just sitting there, gathering dust. Maury started reading them, all of them. He organized teams of assistants to extract the data, wind, current, temperature, and plotted on charts, month by month, region by region. And then he did something even cleverer. He created a standardized form and sent it out to captains all over the world, essentially saying, "If you fill out this form on every voyage and send it back to me, I'll give you a copy of my charts for free." And captains jumped at the deal, because Maury's charts were genuinely useful. They showed you, for any given month, what winds and currents to expect in any part of the ocean. They told you the fastest route. And the results were dramatic. The average sailing time from New York to San Francisco, going all the way around South America, remember? This was before the Panama Canal, dropped from about 180 days to roughly 130 days. That's 50 days shaved off a single voyage, which in commercial terms was enormous. Maury's 1855 book, The Physical Geography of the Sea, is often called the first real textbook of oceanography, and it was a bestseller. People were fascinated. Now, Maury wasn't always right about the mechanisms. He had some ideas about what drove the ocean currents that turned out to be wrong. He overemphasized the role of differences in water density caused by salinity and underestimated the role of wind. But his data was extraordinary, and his basic insight that the ocean had patterns, that those patterns could be mapped, and that understanding them had enormous practical value. That insight was foundational. And here's the thing about Maury that I find particularly poignant. When the Civil War broke out, he sided with the Confederacy. He was from Virginia, and like many Virginians, he felt his loyalty was to his state. He spent the war years in England trying to secure support for the South, and after the war, he went into exile for a while before eventually returning to teach at the Virginia Military Institute. His reputation suffered enormously. The man who had done more than anyone to systematize our understanding of the ocean was, for a time, nearly written out of the story. History is complicated like that. But the work continued without him. And the next great leap in understanding the ocean came from a voyage that was, in many ways, the first purely scientific ocean expedition, the HMS Challenger expedition, which set out from Portsmouth, England, in December of 1872, and didn't return until May of 1876, 3.5 years at sea. Think about that for a second. The Challenger was a Royal Navy corvette, a wooden warship with steam backup, that had been stripped of most of its guns and refitted with laboratories, dredging equipment, thermometers, water sampling bottles, miles of rope, and every scientific instrument the organizers could think of. The driving force behind the expedition was Charles Wyville Thomson, a Scottish naturalist who had already done some deep-sea dredging in the waters around Britain and had found, to everyone's surprise, living creatures at depths where most scientists assumed nothing could survive. The prevailing idea at the time, championed by the influential Edward Forbes, was that below about 300 fathoms, roughly 1,800 feet, the ocean was an azoic zone. Lifeless. Too dark, too cold, too much pressure. Forbes had done dredging in the Aegean Sea in the early 1840s and found that life got sparser as he went deeper, so he extrapolated, reasonably enough, he thought, that it disappeared entirely below a certain point. Thomson proved him wrong, and the Challenger expedition was designed to prove him wrong on a global scale, while also measuring everything else they could think of: depth, temperature, currents, the chemistry of seawater, the composition of the ocean floor. The ship sailed nearly 70,000 nautical miles, crossing the Atlantic multiple times, rounding the Cape of Good Hope, pushing south toward the Antarctic ice, crossing the Pacific. At 362 stations along the way, the crew stopped and took measurements. They lowered thermometers to the bottom on miles of rope. They dredged up sediment and whatever was living in it. They measured the depth by lowering a weighted line until it hit bottom, a process that could take hours in deep water, because you're talking about lowering rope 4 or 5 miles straight down. And it's not always easy to tell when you've hit bottom versus when the rope is just piling up on itself. And what they found was astonishing. Life everywhere. At every depth they sampled, in every ocean, there were organisms. Strange ones, translucent, pressure-adapted, feeding on the slow rain of organic matter drifting down from the sunlit surface. They cataloged over 4,700 new species. They discovered the Mid-Atlantic Ridge, this enormous underwater mountain range running down the center of the Atlantic, though they didn't understand what it was at the time. They mapped the depth of the ocean basins for the first time and found that the Pacific was significantly deeper than the Atlantic. They measured the deepest point they could find in what we now call the Mariana Trench, recording a depth of over 26,000 feet. Not quite the deepest point, which we now know is closer to 36,000 feet, but still staggeringly deep. To put that in perspective, if you took Mount Everest and dropped it into the Mariana Trench, the summit would still be more than a mile underwater. The expedition produced 50 volumes of reports. It took nearly 20 years to publish them all, and Wyville Thomson himself died in 1882, exhausted and in poor health, before the work was finished. His colleague John Murray took over and saw it through. Those 50 volumes became the foundation of modern oceanography, They established baselines that scientists are still comparing against today. And one of the most important things the Challenger expedition revealed, though it took decades for the full implications to sink in, was that the ocean wasn't just a big bathtub of uniform water. It had structure, layers. The temperature measurements showed that the ocean was warm at the surface in the tropics, obviously, but that warmth only penetrated a few hundred feet down. Below that, the temperature dropped rapidly through what we now call the thermocline, this transition zone where you go from warm surface water to the cold, deep water surprisingly fast. And below the thermocline, the entire deep ocean, everywhere in the world, was cold. Close to freezing, in fact. 2, 3, 4 degrees Celsius. Even in the tropics, even directly under the equatorial sun, the deep water was ice cold. Now that's a remarkable thing if you stop and think about it. Where does all that cold water come from? The sun is heating the surface constantly, especially in the tropics. If the ocean were just sitting there passively, you'd expect the heat to gradually work its way down, and the whole ocean would slowly warm up. But it doesn't. The deep ocean stays cold, and the reason is that the ocean isn't sitting there passively at all. It's moving. Not just at the surface, where the wind pushes it around. That's obvious. You can see waves and surface currents. But deep down, in the dark, the ocean is also moving, slowly and relentlessly, in a vast circulation pattern that connects every ocean basin on Earth. And this deep circulation is driven by something completely different from what drives the surface currents. The surface currents are driven primarily by wind. The deep circulation is driven by differences in water density. And water density depends on two things: temperature and salinity. Cold water is denser than warm water. Salty water is denser than fresh water. So when you have water that is both very cold and very salty, it becomes extremely dense, and it sinks. It sinks all the way to the bottom of the ocean, and then it spreads out along the seafloor, creeping slowly. We're talking centimeters per second, maybe a mile or two per day, across the ocean basins. This deep circulation has a name. Oceanographers call it the thermohaline circulation. Thermo for temperature, haline for salt. And the places where this sinking happens, where surface water becomes dense enough to plunge to the bottom, are surprisingly few. There are really only two major regions in the modern ocean where deep water forms in large quantities. One is in the North Atlantic, particularly in the Norwegian and Greenland seas, and in the Labrador Sea between Canada and Greenland. The other is around Antarctica, in the Weddell Sea and the Ross Sea. And the reason these are the spots is fascinating. It's all about what happens to seawater when it gets very, very cold and when sea ice forms. Because here's a detail that matters enormously. When seawater freezes, the ice that forms is mostly fresh. The salt gets expelled, left behind in the surrounding water. So as sea ice forms, the water around it gets saltier, and that saltier, colder water is now extremely dense enough to sink. And when it sinks in the North Atlantic, it forms what oceanographers call North Atlantic deep water, and it flows southward along the bottom of the Atlantic, all the way down past the equator, past South America, and eventually joins the vast cold water masses circling Antarctica. Around Antarctica, the process happens again. The Antarctic bottom water that forms there is actually the densest water mass in the entire ocean, and it creeps northward along the bottom of the Atlantic, the Pacific, and the Indian Ocean, filling up the deep basins from below. And here's where it gets really interesting, because this isn't just a one-way trip. That cold water doesn't just sink and stay down forever. Somewhere, somehow, It has to come back up. Otherwise, you just keep piling cold water into the deep ocean indefinitely, which obviously doesn't happen. The return flow, the upwelling, is much more diffuse and much harder to observe. Some of it happens through slow mixing, where turbulence generated by tides sloshing over rough bottom topography gradually stirs the cold, deep water upward. Some of it happens in specific upwelling zones where winds push surface water aside and deep water rises to replace it. We'll get to those. But the full circuit, from the time a parcel of water sinks in the North Atlantic to the time it eventually returns to the surface somewhere in the Pacific or Indian Ocean, takes roughly 1,000 years. 1,000 years. Water that is right now sitting on the bottom of the Pacific Ocean last saw sunlight during the Middle Ages. That water was at the surface when the Normans were conquering England, when the Song dynasty was flourishing in China, and it has been slowly, silently creeping along the ocean floor ever since, carrying with it the temperature and chemical signature of a world that no longer exists. This whole system, the sinking, the deep flow, the slow return, is sometimes called the global ocean conveyor belt, a term popularized by the geochemist Wallace Broecker of Columbia University in the 1980s. Broecker was one of those scientists who had a gift for making complex ideas accessible, and the conveyor belt metaphor stuck, even though he himself later acknowledged it was a bit too simple. The real circulation is messier, more turbulent, more three-dimensional than a neat conveyor belt suggests. But the basic idea holds. There is a continuous, globe-spanning circulation of water driven by density differences, and it moves an almost incomprehensible amount of water. The Gulf Stream alone, which is part of the surface return flow of this system, carries about 30 million cubic meters of water per second past any given point. That's more than 100 times the combined flow of every river on Earth. And the deep flow, while slower, involves even larger volumes spread across the entire width of the ocean basins. Now, Broecker didn't just describe this circulation. He warned about it. Because one of the things that makes the thermohaline circulation so important and so potentially terrifying is that it appears to have switches. It can change modes. There's evidence in ice cores and ocean sediments that during the last ice age, the circulation pattern was very different from today's, and that it underwent abrupt shifts, changes that happened not over millennia, but over decades, sometimes even years. These shifts appear to be connected to sudden climate changes that were dramatic and severe, swings of 10 degrees Celsius or more in parts of the North Atlantic region within a single human lifetime. Imagine that. You're a farmer in what's now Ireland. Your father farmed the same land, and within the span of a few decades, the climate around you lurches into something almost unrecognizable, winters that never quite end, growing seasons that collapse, ice pushing further south than anyone alive has ever seen. These events have names now. The most famous are called Dansgaard-Oeschger events, named after Willy Dansgaard, a Danish paleoclimatologist, and Hans Oeschger, a Swiss physicist, who independently recognized these rapid oscillations in the ice core records from Greenland in the 1980s. And then there are Heinrich events, named after Hartmut Heinrich, a German marine geologist who in 1988 identified layers of rock debris in North Atlantic sediment cores, debris that had been carried out to sea by massive armadas of icebergs calving off the collapsing ice sheets. These weren't subtle signals buried in noisy data. They were stark, unmistakable layers of stones dropped onto the ocean floor by melting icebergs, thousands of miles from any land. Each Heinrich event represented a catastrophic discharge of ice into the North Atlantic, and each one appears to have disrupted, or even shut down the thermohaline circulation. Here's why that matters so much. When you dump a huge volume of fresh water into the North Atlantic, from melting icebergs, from glacial meltwater floods, you reduce the surface salinity. And if the surface water isn't salty enough, it isn't dense enough to sink, no matter how cold it gets. So the engine stalls. The deep water formation in the Nordic seas slows down or stops. The conveyor belt weakens, and the whole pattern of heat distribution across the planet shifts. Northern Europe, which today is kept remarkably mild by the heat, the Gulf Stream and its extensions carry northward, suddenly loses that warmth, and the effects cascade. Rainfall patterns shift. Monsoons weaken or redirect. Ecosystems on opposite sides of the planet feel the consequences, because the ocean doesn't just connect coastlines, it connects climates. Brooker understood this, and he spent decades warning that the modern thermohaline circulation might be more fragile than we assumed. He called it the Achilles heel of the climate system. His concern was straightforward. If global warming melts enough ice from Greenland and increases freshwater runoff into the North Atlantic, we could nudge the system toward one of those mode shifts. Not necessarily a full shutdown. The models suggest that's unlikely under current projections, but a significant weakening. And in fact, there is some evidence that the Atlantic meridional overturning circulation, which is the more precise term oceanographers use now instead of conveyor belt, has already slowed somewhat over the past few decades. The measurements are tricky, the natural variability is large, and the observational record is short. So there's genuine scientific debate about how much it has weakened and how much of that is due to human activity versus natural fluctuation. But the possibility is taken very seriously. Brooker, who passed away in 2019, spent his final years still pushing this message, that the ocean's deep circulation is not just a curiosity for specialists, but a planetary thermostat that we tinker with at our peril. So let's sit with that for a moment, because it connects to something even bigger. The ocean doesn't just move heat around, it stores it. And this is one of those facts that sounds simple but has enormous consequences. Water, as we talked about earlier, has an extraordinarily high specific heat capacity. It takes a lot of energy to change water's temperature. The ocean is very, very deep on average, about 3,688 meters, which is over 12,000 feet, and it covers 71% of the planet's surface. Put all that together, and you get a heat reservoir of staggering capacity. The top 2.5 meters of the ocean hold as much thermal energy as the entire atmosphere above it. Think about that. A thin skin of water, barely deep enough to wade in, contains the same amount of heat as the whole towering column of air stretching up to the edge of space. The full depth of the ocean? It holds something like 1,000 times more heat than the atmosphere. This is why the ocean is sometimes called the flywheel of the climate system. It absorbs heat slowly, releases it slowly, and smooths out what would otherwise be wild temperature swings. Without the ocean, the difference between day and night temperatures on Earth would be far more extreme, more like what you'd experience on the moon, where daytime surfaces bake at over 100 degrees Celsius, and nighttime surfaces plunge to minus 170. The ocean moderates all of that. Coastal cities have milder climates than inland cities at the same latitude, and this is exactly why. San Francisco and Kansas City are at roughly similar latitudes, but San Francisco's temperature barely varies between summer and winter compared to the brutal swings Kansas City experiences. The Pacific Ocean is sitting right there, breathing thermal stability into the air. Now, here's where this gets really important for understanding the modern moment. Since the middle of the 20th century, As greenhouse gas concentrations have risen, the Earth has been accumulating extra energy, more energy coming in from the sun than radiating back out to space, because the thickening blanket of carbon dioxide and methane traps more of the outgoing infrared radiation. And where has most of that extra energy gone? Not into the atmosphere, actually. Not into melting ice, though that's happening too. More than 90% of the excess heat that has accumulated in the Earth system since the 1970s has been absorbed by the ocean. 90%. The ocean has been quietly, invisibly shouldering almost the entire thermal burden of climate change, and we didn't fully appreciate this for a long time because the temperature increase in the water is spread across such an enormous volume that it's only a fraction of a degree in most places, but a fraction of a degree across 361 million square kilometers of water, extending kilometers deep. That's an almost inconceivable amount of energy. It's equivalent to something like several Hiroshima bombs worth of energy being absorbed every second, day and night, year after year, for decades. And the ocean doesn't just absorb heat, it absorbs carbon dioxide too. This is the other great service the ocean has been performing, largely unnoticed throughout the industrial era. Carbon dioxide dissolves in seawater. It's a simple physical process. Gas molecules at the surface of the ocean are in contact with gas molecules in the atmosphere, and they exchange back and forth until they reach an equilibrium. When we increase the concentration of CO2 in the atmosphere by burning fossil fuels, we push that equilibrium out of balance, and the ocean responds by absorbing more CO2 to try to restore it. The ocean has absorbed roughly a quarter to a third of all the carbon dioxide humans have emitted since the Industrial Revolution. Without this oceanic uptake, atmospheric CO2 levels would be significantly higher than they are today, and the warming we've experienced so far would be considerably worse. But here's the thing, and this is where the story takes a darker turn. When carbon dioxide dissolves in seawater, it doesn't just sit there as a dissolved gas. It reacts with the water to form carbonic acid. It's a weak acid, the same stuff that gives sparkling water its slight tang. But at planetary scale, even a weak acid adds up. The pH of the ocean's surface waters has dropped by about 0.1 units since pre-industrial times. That might sound tiny, but pH is a logarithmic scale, so a 0.1 drop represents roughly a 26% increase in hydrogen ion concentration. The ocean is becoming more acidic, or more precisely, less alkaline, since seawater is still on the basic side of neutral. This process is called ocean acidification, and it's sometimes referred to as the other CO2 problem, the one that gets less attention than warming, but may ultimately be just as consequential. Why does it matter? Because an enormous number of marine organisms build their shells and skeletons out of calcium carbonate, the same mineral that makes up limestone and chalk. Corals do it. Oysters and mussels do it. Tiny planktonic organisms called coccolithophores and foraminifera do it, and these are among the most abundant creatures in the sea. The chemistry of calcium carbonate formation is sensitive to pH. As the water becomes more acidic, it becomes harder for these organisms to build their structures, and in sufficiently acidic conditions, existing calcium carbonate actually starts to dissolve. We're not at that point in surface waters yet, but in some deeper, colder waters, which are naturally more acidic. The saturation horizon, the depth below which calcium carbonate dissolves, is creeping upward. It's getting shallower. Habitats that were once safe for shell-building organisms are becoming corrosive, and this connects to something we haven't talked about yet but should. because it's one of the most extraordinary and underappreciated cycles on the planet. The biological pump. You know how we said the ocean absorbs CO2 at the surface? Well, some of that carbon gets taken up by phytoplankton, those microscopic photosynthetic organisms that float in the sunlit upper layer of the ocean. Phytoplankton are tiny. Most are smaller than the width of a human hair, but collectively they produce roughly half of all the oxygen generated on Earth each year. Half. Every other breath you take, you owe to organisms you've never seen, drifting in seawater. When phytoplankton photosynthesize, they take dissolved CO2 and convert it into organic carbon, their own bodies essentially. And when they die, or when they're eaten and excreted as fecal pellets, or when they clump together into aggregates called marine snow, that organic material sinks. It falls slowly through the water column, and as it sinks, it carries carbon from the surface down into the deep ocean. Some of it gets consumed and recycled on the way down, but a fraction reaches the deep sea floor, where it can be buried in sediments and effectively removed from the atmosphere for geological timescales, millions of years. This is the biological pump, and it's one of the key mechanisms by which the ocean regulates atmospheric CO2 over long periods. But the biological pump doesn't work in isolation. It's intertwined with ocean circulation, with nutrient availability, with temperature, with the very chemistry of the water. And this is what makes the whole system so fascinating and so difficult to predict. Everything connects to everything else. The nutrients that phytoplankton need to grow, nitrogen, phosphorus, iron, silica, are largely supplied by upwelling, by deep water rising back to the surface and bringing those nutrients up from the dark depths where decomposing organic matter released them. So the same circulation patterns we've been talking about, the thermohaline overturning, the wind-driven upwelling along coastlines and at the equator, these are what fertilize the surface ocean and make photosynthesis possible. Without upwelling, the surface ocean would be a nutrient desert, and in fact, large swaths of it are exactly that. The subtropical gyres, those enormous, slowly rotating current systems in the middle of each ocean basin, are sometimes called the deserts of the sea, because the water there is warm, stratified, and nutrient-poor. The phytoplankton can't get what they need, so productivity is low. The water is crystal clear. Beautiful to look at, but biologically sparse. The most productive waters on Earth, by contrast, are the ones where nutrients are being actively delivered to the surface. The coasts of Peru and Chile, where the Humboldt Current drives powerful upwelling. The waters around Antarctica, where deep water surfaces in a great ring around the continent. The North Atlantic in spring, when winter mixing has stirred nutrients up from below, and the returning sunlight triggers explosive phytoplankton blooms that can be seen from space. Vast green swirls hundreds of kilometers across, painting the ocean in colors that shift week by week as different species rise and fall. These blooms are so large and so important that they affect atmospheric chemistry, cloud formation, and even the climate itself, in ways that scientists are still working to fully understand. One of the most surprising connections involves a compound called dimethyl sulfide, or DMS. When certain species of phytoplankton, particularly a group called coccolithophores, those tiny organisms that build their shells out of calcium carbonate, when they're grazed on by zooplankton, or when they die and their cells break apart, they release this sulfur compound into the water. DMS is volatile, which means it escapes from the ocean surface into the atmosphere, and once it's up there, it oxidizes and forms tiny particles called sulfate aerosols. And here's where it gets really interesting. Those aerosol particles act as cloud condensation nuclei. They're the seeds around which water vapor condenses to form cloud droplets. More phytoplankton, more DMS, more aerosol particles, more clouds. And clouds, of course, reflect sunlight back into space, which cools the surface, which affects ocean temperature, which affects phytoplankton growth. You see the loop forming, right? This idea was formalized back in 1987 by a group of scientists, Robert Charlson, James Lovelock, Meinrad Andrea, and Stephen Warren. And it became known as the CLAW hypothesis, named after their initials. Lovelock, you might recognize that name. He's the same James Lovelock who proposed the Gaia hypothesis, the idea that Earth's living systems and physical environment function as a kind of self-regulating whole. And the claw hypothesis was, in a sense, a specific test case for that broader idea. Could biology actually regulate climate through this chain of chemical reactions? Could tiny floating algae influence how many clouds form over the ocean? The answer, it turns out, is complicated. Decades of research since 1987 have shown that the relationship is real. Phytoplankton absolutely do produce DMS, and DMS absolutely does contribute to aerosol formation. But the feedback loop isn't as clean or as strong as the original hypothesis suggested. There are too many other factors involved in cloud formation, too many other sources of aerosol particles, too many nonlinear interactions. But the basic insight stands, and it's a beautiful example of how the ocean's biology and the atmosphere are tangled together in ways that nobody would have guessed a century ago. And this brings us to something that I think deserves real attention, because it's one of the most consequential shifts happening in the oceans right now, and it ties together almost everything we've talked about so far: the warming, the circulation, the chemistry, the biology. I'm talking about ocean stratification. This is one of those concepts that sounds technical, but is actually quite simple. And once you understand it, a lot of other things click into place. Think of the ocean as layers. We've already talked about this a bit. Warm, light water on top, cold, dense water on the bottom, and the thermocline in between acting as a kind of barrier. That layering is stratification. And here's the thing. As the ocean absorbs more heat, the surface layer gets warmer, which makes it lighter, which makes the difference in density between the surface and the deep water even greater. The layers become more distinct, more separated. The warm cap on top gets more buoyant, and it becomes harder for anything to mix across that boundary. Harder for wind to stir nutrients up from below. Harder for surface water to sink and drive the deep circulation. The ocean, in a sense, becomes more rigid, more locked into its layers. And this is not theoretical. This is measured. A study published in 2020, led by a team including Michael Mann and others, analyzed ocean data going back to the 1960s and found that upper ocean stratification had increased by about 5 to 6% over that period. That might not sound like a lot, but in a system this massive, it's significant. More stratification means less vertical mixing, which means fewer nutrients reaching the sunlit surface where phytoplankton need them. And if phytoplankton productivity drops, then the biological pump weakens. Less carbon gets pulled out of the atmosphere and exported to the deep ocean, which means more CO2 stays in the atmosphere, which means more warming, which means more stratification. Another feedback loop, and this one runs in the wrong direction. There's also the oxygen side of this. You might not think of the ocean as needing to breathe, but dissolved oxygen is absolutely critical for marine life, and the ocean gets its oxygen in two main ways. First, from the atmosphere. Oxygen dissolves into surface water from the air, especially in cold, turbulent regions where waves and wind churn the surface. Second, from phytoplankton themselves, which produce oxygen through photosynthesis right there in the upper ocean. But oxygen doesn't stay at the surface. It needs to be transported downward into the deep ocean, and that transport depends on, you guessed it, mixing and circulation. When surface water sinks in the high latitudes, it carries dissolved oxygen with it, ventilating the deep ocean the way opening a window ventilates a stuffy room. So, what happens when stratification increases and circulation slows? The deep ocean gets less oxygen, and this is exactly what's being observed. The global ocean has lost roughly 2% of its dissolved oxygen since the 1960s, and in some regions, the decline is much steeper. These expanding zones of low oxygen, called oxygen minimum zones or sometimes just dead zones, are spreading in the tropical Pacific, the Arabian Sea, the Eastern Atlantic. In the most extreme cases, the oxygen drops so low that almost nothing can survive there. Fish flee if they can. Organisms that can't move simply die. The chemistry shifts to favor anaerobic processes, which can produce hydrogen sulfide, the rotten egg gas, and create conditions that are toxic to most marine life. Now, if this sounds alarming, it should, a little. But it's also worth pausing here and appreciating just how much we've learned about these processes in a remarkably short time. 50 years ago, we had almost no continuous measurements of deep ocean oxygen. We didn't have the satellite coverage to track phytoplankton blooms globally. We didn't have the network of autonomous floats that now drift through the world's oceans, measuring temperature, salinity, and increasingly, biogeochemical parameters like oxygen, nitrate, and pH. That network, by the way, is called ARGO, and it's one of the most impressive observational programs in all of Earth science. It started in the year 2000, and the idea was simple but ambitious. Deploy thousands of robotic floats across every ocean basin. Each float drifts at a depth of about 1,000 meters, and every 10 days it sinks down to 2,000 meters, then rises slowly to the surface, measuring temperature and salinity the whole way up. When it reaches the surface, it transmits its data via satellite, then sinks back down to drift again. As of now, there are nearly 4,000 Argo floats operating worldwide, and they've collectively made over 2 million profiles of the ocean's interior. Before Argo, our picture of the deep ocean was built from ship-based measurements, valuable, but sparse and expensive. A research vessel can only be in one place at a time. Argo gave us something closer to a living, breathing map of ocean conditions, updated in near real time, covering regions that ships rarely visit. And the newer generation of floats, called Biogeochemical Argo, or BGC Argo, carry additional sensors that measure things like dissolved oxygen, chlorophyll, nitrate, pH, and even the optical properties of particles in the water. These floats are giving us our first sustained global view of the ocean's chemistry and biology at depth, and the data they're producing is transforming our understanding of how the ocean's carbon cycle works, how oxygen is distributed, how phytoplankton populations respond to seasonal changes and long-term trends. It's a remarkable thing when you think about it. For most of human history, the deep ocean was essentially unknowable, a vast, dark volume that we could only sample in tiny, disconnected snapshots. And now, we have this fleet of robots quietly patrolling the abyss, reporting back every 10 days, building a picture that gets richer and more detailed with every cycle. It's the kind of patient, systematic observation that Matthew Fontaine Maury would have loved, that the scientists aboard the Challenger would have found almost miraculous. But all that data also confronts us with complexity that can be humbling, because the more we measure, the more we realize how much variability there is, how different one patch of ocean can be from another just a few hundred kilometers away, how conditions at the same location can shift dramatically from one season to the next, how processes operating on timescales of days interact with processes operating on timescales of centuries. And nowhere is that complexity more apparent than when we start looking at the ocean's role in shaping weather and climate on human timescales, the patterns that actually affect whether it rains on your city next month, whether hurricane season will be severe, whether a fishery will thrive or collapse. And the single most famous example of the ocean reaching up and grabbing the atmosphere by the collar, rearranging weather patterns across half the planet, is a phenomenon that fishermen along the coast of Peru noticed centuries before any scientist gave it a name. They called it El Niño, the Christ child, because it tended to arrive around Christmas, bringing warm water and poor fishing to their shores. And what those fishermen were observing, without knowing it, was one end of the largest coupled ocean-atmosphere oscillation on Earth, a cycle that reshuffles heat across the tropical Pacific on a timescale of roughly 2 to 7 years, and in doing so, nudges the entire planet's climate into a different gear. It's called the El Niño Southern Oscillation, or ENSO, and once you understand how it works, you start seeing its fingerprints everywhere, in grain prices in the American Midwest, in wildfire seasons in Australia, in monsoon failures in India, in coral bleaching events across the tropics. It is, without exaggeration, the single most important source of year-to-year climate variability on Earth. And the beautiful thing is that the basic mechanism, once you strip away the jargon, is surprisingly intuitive. So here's the setup. Under normal conditions, what oceanographers call the neutral state, the trade winds blow steadily from east to west across the tropical Pacific. You've got South America on the right side, and Australia and Indonesia on the left, and these persistent easterly winds push the warm surface water westward, piling it up in the western Pacific. And I mean literally piling it up. The sea surface in the western Pacific near Indonesia can sit about half a meter higher than the sea surface near Ecuador. That's a measurable slope in the ocean caused by wind. Now, as that warm water gets shoved westward, cold, nutrient-rich water wells up along the coast of South America and along the equator to replace it. That's the upwelling those Peruvian fishermen depended on. It brought nutrients to the surface, fed the phytoplankton, which fed the anchovies, which fed their families. Meanwhile, over in the western Pacific, all that piled up warm water heats the air above it. The air rises, forms massive convective thunderstorm systems, and dumps enormous amounts of rain on Indonesia, the Philippines, northern Australia. The rising air then flows eastward at high altitude, descends over the cool eastern Pacific, and feeds back into the trade winds at the surface. It's a giant loop, a coupled circulation cell that oceanographers call the Walker circulation, named after Sir Gilbert Walker, a British mathematician who first described the atmospheric pressure seesaw across the Pacific back in the 1920s and 1930s. And here's where Gilbert Walker's story gets interesting, because he was actually looking for something else entirely. Walker had been appointed Director General of Observatories in India in 1904, and his primary obsession was predicting the Indian monsoon. India had suffered catastrophic famines linked to monsoon failures. The Great Famine of 1876 to 1878 killed millions, and the British colonial administration desperately wanted a forecasting tool. Walker was a brilliant statistician, and he started collecting pressure, temperature, and rainfall data from weather stations all over the world, looking for correlations. What he found was this remarkable pattern. When atmospheric pressure was high over the eastern Pacific, it tended to be low over the western Pacific, and vice versa. They seesawed back and forth together. He called it the Southern Oscillation, and he suspected it was connected to monsoon variability, but he couldn't quite prove the mechanism. His colleagues were skeptical. Some of them were openly dismissive. The prevailing attitude was that weather in one part of the world couldn't meaningfully influence weather thousands of miles away. The atmosphere was too chaotic, too local. Walker published his findings, but by the time he retired in 1934, his work was largely ignored. He died in 1958, and it would take another decade before a Norwegian-American meteorologist named Jacob Bjerknes finally connected Walker's atmospheric oscillation to the oceanic phenomenon those Peruvian fishermen had been calling El Niño. Bjerknes showed, in a landmark 1969 paper, that the ocean and the atmosphere weren't separate systems that happened to correlate. They were two halves of a single coupled system, each one driving the other. The warm water caused the atmospheric circulation, and the atmospheric circulation caused the warm water to pile up where it did. It was a feedback loop, and when it broke down, everything shifted. So what actually happens during an El Niño event? The trade winds weaken. Sometimes they don't just weaken. In a strong El Niño, they can actually reverse direction, blowing west to east. And when that happens, all that warm water that's been piling up in the western Pacific, it sloshes back eastward. Think of it like tilting a bathtub. You've been holding the water up at one end, and now you let go. A massive pool of warm water spreads across the central and eastern Pacific. Sea surface temperatures near Peru can jump 2, 3, even 4 degrees Celsius above normal. The upwelling weakens or shuts down entirely, because now there's this thick cap of warm water sitting on top, and the cold, nutrient-rich water can't break through. The fisheries collapse. The phytoplankton disappear. The seabirds that fed on the fish starve. Meanwhile, the center of atmospheric convection, all those big thunderstorm systems, shifts eastward with the warm water. Indonesia and Australia get drought. The central and eastern Pacific get flooding. California can get hammered with storms. The Indian monsoon falters. It's a global rearrangement of where heat and moisture enter the atmosphere, and it all traces back to a change in wind patterns over the tropical Pacific. The 1997 to 98 El Niño was one of the strongest ever recorded, and it gave the world a vivid demonstration of what ENSO can do. Sea surface temperatures in the eastern equatorial Pacific soared more than 5 degrees Celsius above normal. Indonesia and parts of Southeast Asia experienced devastating drought and wildfires. The fires in Borneo and Sumatra were so extensive that the smoke created a persistent haze across the entire region for months. Meanwhile, Peru and Ecuador were hit with torrential rains and catastrophic flooding. East Africa got floods. Southern Africa got drought. The global economic toll was estimated at tens of billions of dollars. And here's the kicker. That event was followed almost immediately by one of the strongest La Niña events on record. Because ENSO has a counterpart, La Niña is essentially the opposite phase. The trade winds strengthen. The warm water gets pushed even more aggressively into the western Pacific. The upwelling along the eastern Pacific intensifies. Sea surface temperatures drop below normal. La Niña tends to bring drought to the American Southwest, enhance Atlantic hurricane activity, and strengthen the Australian monsoon. The system oscillates between these two states, with neutral conditions in between, on that irregular 2 to 7 year cycle. Now, you might be thinking, if we understand the mechanism so well, why can't we predict it perfectly? And the answer gets at something fundamental about how the ocean and atmosphere interact. ENSO is what scientists call a deterministic chaotic system. The physics are well understood, the equations are known, but the system is exquisitely sensitive to initial conditions. Small perturbations, a burst of westerly winds triggered by a tropical cyclone, subtle variations in the depth of the thermocline, interactions with other oscillation patterns, can nudge the system toward an El Niño or a La Niña, or keep it neutral. Modern forecast models can typically predict ENSO state about 6 to 9 months in advance, which is actually remarkable and enormously valuable for agriculture, water management, and disaster preparedness. But beyond that window, skill drops off sharply. There's a predictability barrier, particularly in the northern hemisphere spring. Forecasters call it the spring predictability barrier, when the system seems to reset and become temporarily unreadable. And ENSO doesn't operate in isolation. The Pacific Decadal Oscillation, or PDO, modulates ENSO's behavior on longer timescales of 20 to 30 years. When the PDO is in its positive phase, El Niño events tend to be stronger and more frequent. When it's negative, La Niña dominates. The Atlantic has its own multi-decadal oscillation, the AMO, that influences hurricane activity and Sahel rainfall on timescales of 60 to 80 years. The Indian Ocean has the Indian Ocean dipole, which interacts with ENSO in ways that can either amplify or dampen its effects on the Indian monsoon. These oscillations layer on top of each other like waves in a harbor, sometimes reinforcing, sometimes canceling, creating patterns that can look random if you don't know what you're looking for, but that contain deep structure if you do. And this is where something really subtle and important comes in, something that connects back to the warming and stratification we talked about earlier. Because the question that keeps climate scientists up at night, sometimes literally, is how ENSO will behave as the ocean absorbs more and more heat. Will El Niño events become stronger, more frequent? Will the pattern shift in some fundamental way? The honest answer is that we don't know yet. Climate models disagree. Some project more frequent extreme El Niño events in a warmer world. Others suggest the cycle might weaken. A 2014 study in Nature Climate Change, led by Wenju Kai, found that extreme El Niño events, the kind like 1997 to 98, could become roughly twice as frequent under continued greenhouse gas emissions, driven by faster warming in the eastern equatorial Pacific relative to the surrounding waters. But other modeling groups have reached different conclusions, and the observational record is simply too short to settle the debate statistically. We've only had reliable instrumental measurements of tropical Pacific sea surface temperatures for about 150 years, and truly comprehensive satellite coverage for maybe 40. That's barely enough to capture a handful of full ENSO cycles, let alone detect long-term trends in their behavior. Which brings us to something that might seem like a detour but really isn't. The question of how the ocean stores and moves heat not just horizontally, across the surface, but vertically, into the deep. Because one of the great puzzles of the early 21st century was a period, roughly 1998 to 2012, when global surface temperatures seemed to plateau, even though greenhouse gas concentrations kept rising. Climate skeptics seized on it, calling it a hiatus or a pause, and using it to argue that climate models were wrong. But oceanographers suspected something else was happening. They thought the heat was still accumulating. It was just going somewhere the surface thermometers couldn't see it. It was going into the deep ocean, And the evidence for this came from, you guessed it, those Argo floats we talked about, along with increasingly sophisticated satellite measurements of Earth's energy imbalance. What researchers found was that during that period, the Pacific trade winds had actually strengthened, a La Niña-like pattern, pushing more warm water into the western Pacific and driving enhanced heat uptake into the subsurface ocean. The planet was still gaining energy. The ocean was just hiding it below the surface, tucking it away at depths of 300, 500, 700 meters. And when the pattern eventually shifted and a massive El Niño developed in 2015 to 16, some of that stored heat came roaring back to the surface and global temperatures spiked to new records. Think about what that means for a moment. The ocean isn't just passively absorbing heat like a sponge. It's actively redistributing it, storing it, releasing it, on timescales that can fool you into thinking the climate has stopped changing, when really, it's just loading the spring for the next jump. The deep ocean is a reservoir with a memory that operates on timescales far longer than human attention spans, decades, centuries. Heat that enters the deep ocean today might not return to the surface for hundreds of years. That's a commitment. That's inertia built into the system that no policy change can quickly reverse. And that deep storage connects to another phenomenon that's been getting increasing attention, one that operates on even grander spatial scales than ENSO and touches every coastline on the planet. It's the question of sea level. Not just how much the ocean is rising, but why it rises unevenly, why some coastlines are experiencing rates of rise 3 or 4 times the global average, while others are barely changing at all. And the answer involves a surprisingly complex interplay of thermal expansion, ice sheet dynamics, ocean currents, gravitational effects. Yes, gravitational effects, because ice sheets are so massive that they actually pull the ocean toward them with their own gravity. And when they melt, the ocean doesn't just rise uniformly. It actually falls near the melting ice and rises more than average on the opposite side of the planet. It's counterintuitive and fascinating, and it starts with a simple physical fact about water that you've probably noticed 100 times without thinking about it. When you heat water, it expands. You've seen a pot of water on the stove. The level creeps up slightly as it warms. It's a tiny effect for a small volume, barely noticeable. But here's the thing about the ocean. It's not a small volume. The ocean contains roughly 1.335 billion cubic kilometers of water. So even a tiny amount of thermal expansion spread across that incomprehensible volume adds up to a measurable rise in sea level. And this is the part that surprises most people. Thermal expansion alone, just the water getting slightly less dense as it warms, accounts for about 1/3 to 40% of the sea level rise we've observed over the past century. No ice melting required, just warmer water taking up more space. Now, the global average sea level has risen about 20 centimeters, roughly 8 inches, since 1900, and the rate is accelerating. In the early 20th century, it was maybe 1.2 millimeters per year. By the 1990s, it had climbed to about 2.5 millimeters per year. And satellite altimetry, which has been measuring sea level with extraordinary precision since the Topek/Poseidon mission launched in 1992, shows the current rate is around 3.6 millimeters per year and still climbing. That might sound small, 3.5 millimeters, but multiply that across decades and you start to understand why coastal planners are losing sleep. At current rates, we're looking at another 30 centimeters or more by the end of this century, and if ice sheet contributions accelerate, which many glaciologists think is increasingly likely, it could be considerably more than that. But here's where it gets really interesting, and where the engineering of understanding the ocean gets genuinely complicated. Sea level doesn't rise like water filling a bathtub. It's not uniform. If you look at a map of sea level trends measured by satellite, and there are beautiful ones produced by NASA and CNEs, you see a patchwork. Some regions of the ocean have risen 10 or 12 millimeters per year over the past 3 decades. Others have barely risen at all. A few spots have actually dropped. The western tropical Pacific, for instance, experienced rates of rise roughly 3 times the global average during the period from about 1993 to 2012. Meanwhile, parts of the eastern Pacific rose much more slowly. And the reason for that particular pattern? Trade winds. During that same period, strengthened trade winds, the same ones we talked about when discussing the so-called global warming hiatus, were piling warm water up in the western Pacific, literally pushing it westward and raising sea level there while suppressing it in the east. When those trade winds relaxed during the 2015-16 El Niño, some of that imbalance corrected. So ENSO, which we spent all that time exploring, is directly shaping which communities flood and which don't on timescales of years to decades. But trade winds are only one piece of the puzzle. Ocean currents matter too. Changes in the Gulf Stream, for example, have been linked to accelerated sea level rise along the northeastern coast of the United States. There's a stretch from Cape Hatteras up to Boston where sea level has been rising 3 to 4 times faster than the global average since about 2010. Part of the explanation involves a slowing of the Gulf Stream system, that Atlantic meridional overturning circulation we discussed earlier, the Great Conveyor. When the Gulf Stream slows down, the Coriolis effect that normally pulls water away from the coast weakens, and water piles up along the shoreline. It's a dynamic effect, driven by changes in ocean circulation, and it means that a city like Norfolk, Virginia, or Miami, or even New York, faces a different sea level future than a city on, say, the coast of Chile, even though they share the same ocean. And then there's the gravitational fingerprint, which is genuinely one of the most counterintuitive things in all of Earth science. Picture the Greenland ice sheet. It's enormous, about 2.85 million cubic kilometers of ice, roughly 1.7 million square kilometers in area, up to 3 kilometers thick in places. That's a lot of mass, and mass generates gravity. So the Greenland ice sheet is actually pulling the surrounding ocean toward itself, piling water up along nearby coastlines, Greenland's own coast, Iceland, Northern Europe. Now, when that ice sheet loses mass, and it's been losing mass at an accelerating rate, roughly 280 billion tons per year in recent years, 2 things happen. First, that meltwater flows into the ocean and adds volume. But second, and this is the wild part, the gravitational pull of the ice sheet weakens. The ocean that was being pulled toward Greenland starts to relax away from it. Sea level actually falls near Greenland and rises more than the global average on the far side of the planet. For Greenland ice loss specifically, the places that get the most sea level rise are in the southern hemisphere, South America, the southern Indian Ocean, parts of the Pacific. Meanwhile, if it's the West Antarctic ice sheet that's melting, the gravitational fingerprint is roughly the opposite. Sea level rise is amplified in the northern hemisphere. This was worked out theoretically decades ago, but it was a physicist named Jerry Mitrovica at Harvard who really brought gravitational fingerprinting into the modern climate conversation, showing that you could potentially use precise measurements of regional sea level patterns to figure out which ice sheets are contributing how much meltwater. It's like forensic accounting for the ocean. Each ice sheet leaves a unique spatial signature, And if your measurements are good enough, you can decompose the observed pattern and attribute the contributions, and your measurements are getting good enough. Between satellite altimetry, measuring the ocean surface, the grace and grace follow. On satellite missions, measuring changes in Earth's gravitational field directly, literally weighing the ice sheets from space, and the Argo network providing temperature and salinity profiles that let you calculate thermal expansion, scientists can now close the sea level budget with reasonable precision. They can say, this much came from thermal expansion, this much from Greenland, this much from Antarctica, this much from mountain glaciers, this much from changes in land water storage. And the numbers add up. That's a remarkable achievement because for a long time they didn't add up and the discrepancy was a genuine puzzle. But knowing where the water is coming from is different from knowing where it's going, and that's where the engineering challenge meets the human challenge. Because sea level rise isn't really an ocean problem. It's a coastline problem. And coastlines are where people live. Something like 600 million people live in coastal zones less than 10 meters above current sea level. Entire nations, the Maldives, Tuvalu, Kiribati, the Marshall Islands, have maximum elevations of just a few meters. For them, even the moderate projections of sea level rise represent an existential threat. Not a metaphorical existential threat, an actual one. Their countries could become uninhabitable within the lifetimes of children born today. And even in wealthier nations with more resources for adaptation, the engineering challenges are staggering. Think about what sea level rise actually does to a coastline. It's not just about permanent inundation, though that's the dramatic image most people picture. Before any land is permanently submerged, you get increased flooding during storms and high tides. You get saltwater intrusion into freshwater aquifers, the underground reservoirs that millions of people depend on for drinking water. You get accelerated erosion. You get damage to infrastructure that was designed for a different sea level: roads, sewers, electrical systems, foundations. Miami Beach has already spent hundreds of millions of dollars installing pump systems to deal with tidal flooding that simply didn't happen a few decades ago. The Netherlands, of course, has been engineering its relationship with the sea for centuries. The Dutch have an almost unparalleled tradition of water management with their system of dikes, storm surge barriers, and polders. The Maaslandkering, the massive storm surge barrier protecting Rotterdam, is one of the largest moving structures on Earth. Two enormous steel arms that swing closed when storm surges threaten. It was completed in 1997 and designed with a specific set of assumptions about how often it would need to close. Those assumptions are already being revised upward. And this brings up something that engineers and climate scientists increasingly talk about, which is the concept of committed sea level rise, the amount of rise that's already locked in by warming that has already occurred, regardless of what we do with emissions going forward. Remember that deep ocean heat storage we talked about? Heat that's already been absorbed by the ocean will continue to cause thermal expansion for centuries. Ice sheets respond slowly to warming. They're not going to stop losing mass the moment temperatures stabilize, because the warmer ocean water that's already undercutting their marine terminating glaciers will keep doing so for a long time. Current estimates suggest that even if we somehow held global temperatures at present levels, we'd still be looking at something like 0.5 meter to 1 meter of additional sea level rise over the coming centuries just from commitments already made. And if warming continues, the numbers get much larger. The big uncertainty, the one that keeps ice sheet scientists up at night, is the marine ice sheet instability mechanism in West Antarctica, where warming ocean water could trigger an irreversible retreat of glaciers grounded below sea level, potentially contributing several meters of rise over centuries. Several meters. That would reshape the map of the world. So the ocean is rising, unevenly, with a memory that extends far beyond any human planning horizon. And it's changing in other ways too, ways that connect back to everything we've been talking about. The warming, the acidification, the deoxygenation, the shifts in circulation. All of these changes converge in the ecosystems that depend on the ocean, and nowhere is that convergence more visible, more heartbreaking, and more scientifically instructive than in coral reefs. Coral reefs occupy less than 1% of the ocean floor, but they support roughly a quarter of all marine species. They protect coastlines from wave energy. They sustain the livelihoods of something like 500 million people. And they are exquisitely sensitive to the very changes we've been describing: temperature, pH, oxygen levels. The phenomenon that's been getting the most attention is coral bleaching. And to understand why it happens, you need to understand one of the most remarkable symbiotic relationships in nature. Inside the tissue of a healthy coral polyp. And remember, a coral is an animal, not a rock, not a plant, but a tiny soft-bodied animal related to jellyfish and sea anemones. Inside that tissue live millions of microscopic algae called zooxanthellae. These are single-celled photosynthetic organisms, dinoflagellates specifically, and they've struck up a deal with the coral that's been running successfully for something like 200 million years. The algae get a safe place to live, sheltered inside the coral's tissue, with access to the coral's metabolic waste products: carbon dioxide, nitrogen, phosphorus, which the algae use as nutrients. In return, the algae photosynthesize, and they pass up to 90% of the sugars they produce directly to the coral host. 90%. That's an extraordinarily generous arrangement, and it's the reason corals can thrive in the nutrient-poor tropical waters where you typically find reefs. The water is clear and blue precisely because there's very little plankton or dissolved nutrients in it. It's basically a marine desert, and yet these reefs are teeming with life. The zooxanthellae are the engine that makes the whole thing possible. They're also what give corals their color. A healthy coral gets its greens, its browns, its golds, its subtle purples from the pigments inside those algae cells. Now here's what happens when the water gets too warm. When temperatures rise just 1 to 2 degrees Celsius above the normal summer maximum, and we're talking about sustained warmth, a few weeks of it, the zooxanthellae start malfunctioning. The heat disrupts their photosynthetic machinery, and instead of producing useful sugars, they begin generating reactive oxygen species, essentially toxic byproducts. The coral, sensing this chemical stress, does the only thing it can. It expels the algae. It ejects its own food source. And what you're left with is the coral's transparent tissue, draped over its white calcium carbonate skeleton. That ghostly white appearance is what we call bleaching. The coral isn't dead yet, not immediately, but it's starving. It can survive for a few weeks in this state, maybe a couple of months if conditions are favorable, pulling energy from whatever zooplankton it can catch with its tiny tentacles. But if the water doesn't cool down, if the algae don't recolonize, the coral dies. And this isn't a hypothetical. This is happening right now, at a scale that would have seemed unimaginable a few decades ago. The first truly global mass bleaching event was recorded in 1998, and you might remember, that was the year of the massive El Niño we talked about earlier, the one that pushed global temperatures to what was then a record. Reefs across the Pacific, the Indian Ocean, the Caribbean, all bleached simultaneously. Some estimates suggest that about 16% of the world's shallow water corals died in that single event. 16% in 1 year. Then it happened again in 2010, Again in 2014 through 2017, that third global bleaching event lasted 3 full years, the longest ever recorded, hammering the Great Barrier Reef in back-to-back summers of 2016 and 2017. Aerial surveys showed that, in 2016 alone, about 30% of the corals on the Great Barrier Reef died, and then 2020 brought another mass bleaching to the same reef, and 2022, and 2024. The intervals between these events are getting shorter, and that matters enormously because coral recovery takes time. A decade at minimum for fast-growing species, much longer for the slow, massive corals that form the structural backbone of a reef. If bleaching events come faster than recovery, you get a ratchet effect. Each event pushes the reef further down, and it never fully comes back before the next hit arrives. Here's the thing that makes this especially poignant from an engineering perspective, and I use that word loosely because what corals do is really biological engineering of the highest order. A coral reef is a self-assembling, self-repairing structure built from calcium carbonate that the coral polyps secrete, molecule by molecule, over centuries and millennia. The Great Barrier Reef stretches over 2,300 kilometers along the northeast coast of Australia. It's visible from space, and it was built by animals the size of a pencil eraser. The structural complexity of a reef, all those nooks, crevices, overhangs, caves, channels, is what creates habitat for the extraordinary diversity of fish, invertebrates, and algae that live there. When the coral dies and the skeleton erodes, that complexity collapses. You go from a three-dimensional cathedral to a flat rubble field, and the fish and everything else that depended on that structure disappear with it. And bleaching isn't the only threat. Remember the acidification we talked about? The ocean absorbing CO2 and its pH dropping? That hits coral reefs in a completely different way. Corals build their skeletons from aragonite, a form of calcium carbonate, and the rate at which they can do that depends on the saturation state of aragonite in the surrounding seawater. As the water becomes more acidic, the saturation state drops, and it gets harder for corals to build. It's like trying to construct a wall while someone is slowly dissolving the mortar. Below a certain threshold, and some tropical waters are projected to cross it by mid-century under high-emission scenarios, the water actually becomes corrosive to existing coral skeletons. The reef doesn't just stop growing, it starts dissolving. You can see this already in certain naturally acidified environments, like the volcanic CO2 seeps off Papua New Guinea and off the Italian island of Ischia, where bubbles of carbon dioxide percolate up through the seafloor and locally lower the pH. Dive at those sites, and you see what a high CO2 ocean looks like. The corals thin out, the reefs simplify, the diversity drops. It's a window into a possible future. So you've got warming causing bleaching, acidification undermining the skeleton, deoxygenation stressing the metabolism, and on top of all that, the usual local pressures: overfishing, sediment runoff from coastal development, nutrient pollution that feeds algae blooms that smother coral. These stressors don't just add up, they multiply each other. A coral that's already weakened by bleaching is less able to cope with acidification. A reef that's lost its herbivorous fish to overfishing can't control the algae that compete with coral for space. It's a cascade, and it's why reef scientists have been sounding the alarm so urgently. But here's where the story gets complicated, because nature is never as simple as we'd like. Not all corals respond the same way. Some species are more heat-tolerant than others. Some reefs in naturally variable environments places where temperatures swing widely with the tides or the seasons, seem to harbor corals that are pre-adapted to handle thermal stress. Researchers like Ruth Gates at the Hawaii Institute of Marine Biology, before her untimely death in 2018, were actively working on what she called assisted evolution, selectively breeding heat-tolerant coral strains and exploring whether you could inoculate corals with tougher varieties of Zooxanthellae. It's a kind of biological engineering, trying to accelerate adaptation that might otherwise take thousands of years. Other groups are experimenting with coral gardening, growing coral fragments in underwater nurseries and transplanting them onto degraded reefs. In the Florida Keys, the Coral Restoration Foundation has outplanted over 100,000 corals. It's painstaking, hands-on work, and it can't possibly scale to the size of the problem globally, but it buys time for individual reefs and preserves genetic diversity. There's also the deeper question of whether some reefs might migrate. As tropical waters become too warm, could corals establish new reefs at higher latitudes, in waters that were previously too cool? There's actually some evidence this is happening. Coral species showing up in places like Japan's temperate zone, or along the coast of southeastern Australia, further south than they've been recorded before. But migration isn't straightforward. The corals need the right substrate, the right light levels, the right water chemistry, and they need to get there, which means their larvae have to survive the journey on ocean currents. And the existing ecosystems at those higher latitudes, like kelp forests, have their own ecological value. It's not a clean swap. So what does all this mean for the 500 million people whose livelihoods depend on reefs? For the coastal communities that rely on reef structures to buffer storm waves? For the fisheries, the tourism, the cultural identity tied to these ecosystems? This is where oceanography stops being abstract science and becomes something deeply, urgently human. The Intergovernmental Panel on Climate Change has been quite blunt about this. At one point, 5 degrees Celsius of global warming, they project that 70 to 90% of tropical coral reefs will be lost. At 2 degrees, the number rises to more than 99%. Those aren't distant projections. We're already at about 1.2 degrees above pre-industrial levels, and coral reefs are just the most visible example of a broader transformation happening across ocean ecosystems. Think about the base of the food web, the phytoplankton. These microscopic organisms produce roughly half of all the oxygen on Earth, and they're the foundation of virtually every marine food chain. Their distribution and abundance depend on light, nutrients, and temperature, all of which are shifting. As the surface ocean warms and stratifies, remember, we talked about that layering effect, the warm water sitting on top of the cold, nutrient-rich water below. The supply of nutrients to the sunlit surface layer gets choked off. In the subtropical gyres, the vast, slow-spinning current systems that cover huge swaths of the ocean, satellite observations suggest that chlorophyll concentrations have been declining, meaning less phytoplankton. Some studies estimate a global decline of about 1% per year over the past few decades, though the data is noisy and the trends are debated. But even a modest decline in phytoplankton productivity has enormous implications because it propagates up through the food web. Less phytoplankton means less zooplankton, which means fewer small fish, which means fewer big fish, which means less food for seabirds and marine mammals and, ultimately, for us. Meanwhile, other parts of the ocean are seeing changes in the opposite direction. In the Arctic, as sea ice retreats, sunlight reaches water that was previously covered year-round, triggering massive phytoplankton blooms in areas where they were rare before. The timing of these blooms is shifting too, which creates mismatches. The zooplankton that evolved to reproduce when the bloom peaks may find themselves hatching too early or too late, missing the food pulse they depend on. These phenological mismatches ripple through the ecosystem in ways that are hard to predict. And then there are the species on the move. As ocean temperatures shift, marine organisms are migrating, generally poleward toward cooler water and generally faster than terrestrial species. Fish stocks that have supported communities for generations are showing up in new places. Atlantic mackerel, for instance, have shifted northward into Icelandic and Faroes waters over the past couple of decades, sparking international fishing disputes because the fish crossed political boundaries that the quota agreements never anticipated. Lobsters in the Gulf of Maine have boomed as waters warmed, but the same warming has devastated lobster populations further south in Long Island Sound. Species are reshuffling, and the ecological communities that result are ones that have no historical analog, combinations of species that have never coexisted before, interacting in ways we can't fully predict. This reshuffling extends to the deep ocean too, though we know far less about it because the deep sea remains one of the least explored environments on Earth. And that brings us to something that's been gaining attention in recent years: the prospect of deep sea mining, and what it reveals about how much we still don't understand about the ecosystems that exist down there in the permanent dark. Because here's the thing. When we talk about the ocean, most of what we've been exploring together tonight has been about the upper layers, the sunlit zone, the first couple hundred meters where photosynthesis happens and where most of the life we're familiar with lives. But the deep ocean, the abyssal plains that stretch across something like 60% of Earth's solid surface, those are realms we've barely touched. We've mapped the surface of Mars in better resolution than we've mapped our own ocean floor. Let that sit for a second. The planet next door, tens of millions of miles away, and we know its topography more intimately than we know the bottom of our own seas. And now there's a growing push to go down there, not to explore exactly, but to extract. Deep-sea mining targets polymetallic nodules, those potato-sized lumps of manganese, nickel, cobalt, and copper that sit scattered across the abyssal plains, particularly in a region called the Clarion-Clipperton Zone between Hawaii and Mexico. These nodules formed over millions of years, growing at rates of maybe a few millimeters per million years, accreting metal oxides layer by infinitesimal layer around a seed, a shark tooth, a bit of bone, a fragment of shell. They're among the slowest growing geological objects we know of, and they contain metals that modern technology is hungry for, the same metals that go into batteries for electric vehicles, into smartphones, into wind turbines. There's a real irony there. The technologies we're building to address climate change require materials that might only be accessible by disrupting one of the last untouched ecosystems on the planet. The International Seabed Authority, the ISA, which is the UN body responsible for managing mineral resources in international waters, has been working on regulations for years. As of the mid-2020s, no commercial deep-sea mining has been approved, but exploration contracts have been granted, and the pressure is building. The nation of Nauru triggered a provision in 2021 that gave the ISA a 2-year deadline to finalize mining regulations. And when that deadline passed without completed rules, the legal situation became genuinely murky. Companies like the Metals Company have been pushing forward with pilot collection tests, scooping up nodules from the seafloor and bringing them to the surface. And here's what we don't fully understand. What happens to the ecosystem when you do that? The abyssal plains might look barren at first glance, like muddy deserts, but they're not. They host communities of organisms that are adapted to conditions almost unimaginable to us. Near freezing temperatures, pressures hundreds of times what we experience at the surface, total darkness, and vanishingly little food. Just a slow rain of organic particles drifting down from the productive surface waters above, what oceanographers poetically call marine snow. The creatures down there, xenophyophores, polychaete worms, tiny crustaceans, bizarre soft-bodied organisms that we haven't even classified yet. They live slow lives. They grow slowly, reproduce slowly, and many of them depend on those very nodules as hard substrate in an otherwise soft, muddy world. Remove the nodules, and you remove their habitat. Disturb the sediment, and you create plumes that can drift for hundreds of kilometers, smothering filter feeders and altering the chemistry of the water column in ways we're only beginning to model. A major study published in 2023 from the Clarion-Clipperton Zone found that roughly 70 to 90% of the species collected were new to science. Think about what that means. We're contemplating industrial-scale extraction from an environment where we can't even name most of the inhabitants. It's a bit like bulldozing a rainforest before you've cataloged the trees, except this particular forest took millions of years to grow and won't grow back on any timescale meaningful to human civilization. But the deep-sea mining debate is really a microcosm of a much larger question, one that runs through everything we've been talking about tonight. How do you make decisions about a system you don't fully understand? And the honest answer, the one that keeps oceanographers up at night, even when they're not lying in the dark thinking about thermohaline circulation, is that we've been making those decisions all along, whether we meant to or not. Every ton of carbon dioxide we've emitted has been a decision about ocean chemistry. Every degree of warming has been a decision about coral reefs and ice sheets and the Atlantic meridional overturning circulation. We just didn't frame them as decisions at the time. And that's what makes the ocean sciences so urgent right now, in a way they've never quite been before. For most of human history, the ocean was so vast, so deep, so apparently inexhaustible that the idea of fundamentally altering it seemed absurd. Matthew Fontaine Maury, back in the 1850s, saw the ocean as a system to be charted and harnessed. The scientists aboard HMS Challenger in the 1870s saw it as a frontier to be catalogued. Even through most of the 20th century, the ocean was treated as a sink, a place where you could dump waste, extract fish, and assume it would absorb whatever you threw at it. The sheer volume seemed to guarantee resilience. 332 million cubic miles of water. How could anything we do make a dent? But we've seen, over and over tonight, how that assumption was wrong. The ocean has absorbed roughly a third of all the carbon dioxide humanity has produced since the Industrial Revolution, and the result is that its pH has dropped by about 0.1 units, which sounds tiny until you remember that the pH scale is logarithmic. So that represents roughly a 30% increase in hydrogen ion concentration. The ocean has absorbed more than 90% of the excess heat trapped by greenhouse gases, and that heat is now working its way into the deep water, expanding the volume of the seas, destabilizing ice sheets, shifting the habitats of countless species. The great conveyor belt of thermohaline circulation, which Wallace Broecker warned us about decades ago, is showing signs of weakening. The corals are bleaching on a schedule that no longer allows recovery. The phytoplankton that produce roughly half the oxygen you breathe, those tiny, invisible organisms that most people never think about, are responding to changes in stratification and nutrient supply in ways that could reshape the base of the entire marine food web. And yet, there's something else that runs through this story too. Something quieter, but just as real. And it's worth holding on to as you lie there letting your thoughts soften. It's the sheer persistence of human curiosity about the ocean. The Polynesians who read the swells and the stars to cross thousands of miles of open Pacific. Eratosthenes measuring the angle of shadows to figure out the size of the earth. Benjamin Franklin asking whaling captains about the Gulf Stream and sketching out the first chart. The crew of the Challenger spending 3.5 years hauling dredges up from the abyss, cataloging species by lamplight. Wally Broker, chain smoking in his office at Lamont Doherty, connecting ice cores to ocean circulation and seeing a future that most people didn't want to think about. Ruth Gates, dreaming of corals tough enough to survive a warming world. The engineers who designed the Argo floats, 4,000 of them, drifting through the global ocean right now, tonight, as you listen to this, rising and sinking and transmitting data about temperature and salinity from depths of 2,000 meters, painting a picture of the ocean's interior that would have been unimaginable a generation ago. That curiosity hasn't stopped. If anything, it's accelerating. We're using satellite altimetry to measure sea level to within a few millimeters. We're deploying autonomous underwater gliders that can patrol the deep ocean for months at a time. We're using environmental DNA, traces of genetic material that organisms shed into the water, to detect species without ever seeing them, sampling a liter of seawater and reading it like a census of everything that swam through recently. We're building coupled climate models that simulate the ocean and atmosphere together. Models that are imperfect but getting better with every generation. And we're using them to ask the kinds of questions that matter most. How much warming is already locked in? Where will the water rise fastest? Which fisheries will collapse and which will shift? What happens to the AMOC if Greenland keeps melting at the rate it's going? These aren't abstract questions. They're questions about real places and real lives. About the family in Bangladesh whose home sits a meter above current sea level. About the fisherman in Maine whose grandfather caught cod, but whose livelihood now depends on lobster that may soon move further north. About the island nations of the Pacific, Tuvalu, Kiribati, the Marshall Islands, whose entire existence is a negotiation with the ocean, and who are already planning for a future in which their land may be uninhabitable. The ocean doesn't care about national borders or economic models or political cycles. It responds to physics. It responds to chemistry. It does what the laws of thermodynamics and fluid dynamics say it will do, and it does it on its own timescale, which is both a mercy and a danger. A mercy because changes unfold slowly enough for us to observe and respond. A danger because by the time the changes are obvious, the momentum behind them may be enormous. So, what do you do with all of this? What's the takeaway, if there is one, from this long, wandering conversation about water and salt and heat and life? Maybe it's this. The ocean is the largest, most complex, most consequential system on the planet that most people rarely think about. It regulates your climate. It feeds billions of people. It produces much of the oxygen in the air you're breathing right now. This very breath, as you lie there getting sleepy. It connects every continent, every ecosystem, every weather pattern. It has a memory, a long one, encoded in the slow circulation of deep water that won't surface again for 1,000 years, carrying with it a record of the temperature and chemistry of the world as it was when that water last touched the atmosphere. The decisions we make in the next few decades will be written into that memory. They'll be carried in the deep currents, dissolved in the chemistry, recorded in the growth rings of corals that haven't been born yet, reflected in the species that survive and the ones that don't. But the ocean is also, still, astonishingly beautiful and astonishingly alive. Bioluminescent plankton lighting up a wave at night like scattered stars. Humpback whales singing songs that travel hundreds of miles through the deep sound channel. The quiet, patient work of a coral polyp, smaller than your fingernail, laying down its skeleton grain by grain, building a reef that will shelter thousands of species. The midnight zone, where creatures carry their own light through water that has never seen the sun. There's wonder in it. Real, genuine, inexhaustible wonder. And that's maybe the best thing to fall asleep to. The knowledge that right now, tonight, while you're lying here warm and still, the ocean is doing all of it. The currents are flowing. The thermohaline conveyor is turning over, slowly, patiently, the way it has for millions of years. Somewhere in the Pacific, an Argo float is sinking through the thermocline, measuring the temperature of water that won't see daylight for centuries. Somewhere in the tropics, a coral polyp is feeding in the dark, its tiny tentacles catching particles of marine snow. Somewhere in the Southern Ocean, cold Antarctic bottom water is sliding down the continental shelf, beginning a journey along the ocean floor that will take it around the world. The tides are rising and falling, pulled by the same moon that's probably visible through your window if you opened your eyes, though you don't need to. The whole system is breathing, in its slow, planetary way, the way it has since those first rains fell on cooling basalt 4 billion years ago and began to fill the basins. It's all still going, and there are people, thousands of them, all over the world, who have devoted their lives to understanding it, to watching over it, to figuring out how it works and what it needs and how we can do better by it. That work goes on too, quiet and steady, like the currents themselves, and maybe that's enough to carry you into sleep. The thought of all that water, all that motion, all that life, all that slow and patient complexity, doing what it does, being what it is, the ocean, the original ocean, the one that made everything else possible, still here, still vast, still full of secrets we haven't found yet, still worth knowing, still worth caring about, still breathing slow and deep, just like you.